All right. Good evening, everyone. I'm sure people are slowly coming in, and we'll do a brief introduction as people join us. So welcome. Welcome everyone to the second in a series of free presentations on the James Webb Space Telescope offered to you by the Christa McAuliffe Center for Integrated Science Learning. My name is Irene Porro, and I am a director of the Christa McAuliffe Center. I'm so delighted to be your host tonight. So to start, I would like actually to remind all of you that our in-person programs at the Framingham State Planetarium will resume next week with the screening of several planetarium films during what we call the planetarium movie days. For more information and about the calendar and the times of the shows, please visit our website. And I think Suzanne will post it in the chat, it's cmcenter.org/movie days. Also, I want to remind you that our regular in-person monthly public planetarium shows will resume in September. For a calendar of events, you may want to check the link again posted in the chat box that will take you directly to the schedule of the public planetarium shows. Now, the exciting news is not just that we are resuming our in-person programs, but our virtual monthly presentations will also continue. So, the focus of our in-person and virtual presentation will be a bit different so that everyone will find something of interest to them. Exploration of the night sky will be done in a physical planetarium where they're done in the best way possible. A virtual presentation will instead focus on specific topics in space science and astrophysics, like the talk we are offering tonight. So you, of course, are welcome to attend both in-person and virtual events, or you can choose a medium that you prefer to keep engaging with our team of great presenters. Now, about tonight. As we mentioned, we continue our introduction to the James Webb Space Telescope. Webb will be the largest, the most powerful and complex space telescope ever built and ever launched into space. If everything goes well, its launch is scheduled for the end of October 2021, so very soon. With a segmented mirror extending more than 19 feet across, a sun shield the size of a tennis court, this gigantic observatory is folded up for launch and unfurls as it travels to its final orbit 1 million miles away. Webb was designed to see the first galaxies forming shortly after the Big Bang, but its infrared sensitivity allows it to peer into dusty environments, making it the perfect instrument to explore the regions where stars and planets form and to trace how galaxies have evolved over time. Webb's potential is so transformative for astronomy that 3 international space agencies, NASA, the European Space Agency, and the Canadian Space Agency, have partnered together to bring it to launch. So it's really a special mission. So if you joined us last month, you may remember that at that time we introduced our audience to the telescope and its science goals. If you couldn't join us last time, you can see actually a recording of that presentation on our YouTube channel. Tonight, we will focus a little bit more on the engineering aspects of the observatory to understand what spatial design and engineering strategies had to be developed to make sure that Webb can do the revolutionary science and research that we are expecting it to do. Finally, though, in September, we will explore in this series we are offering tonight, we will explore the new science that the researchers are again expecting to do, and that will the new discoveries that we hope they will make. And finally, really, I want to stress a big event we are going to host in October, on October 15th. We will host a special event for the launch, in preparation for the launch of the Webb in the FSU Planetarium with Dr. Catherine Flanagan from a Space Telescope Science Institute as the keynote speaker. I know I gave you a lot of dates and events to remember. Just to check all our events, dates and times, please go to our website, the cmcenter.org at planetarium/public, and you will be able to figure out all this when you want to tune in with us for all these special events. Okay, time to get to tonight. First of all, I just want to remind everyone, as we usually do, to keep your questions for the end of a presentation and then post them in a Q&A box that you can find in the bottom right of your Zoom window. I'm very happy now to welcome back our speaker, John Sheff. As you may recall, John is a NASA JPL Solar System Ambassador, and we are very lucky that he's also a program facilitator here at the Christa McCauley Center. He is a member of the Amateur Telescope Makers of Boston, and among many other things he does, he operates the telescopes during public nights at the Harvard-Smithsonian Center for Astrophysics in Cambridge. But now I want to welcome back John, and the screen and the mic are all yours.
Thank you very much, Irene. That's a wonderful introduction. And as you mentioned, today we will be talking about the nuts and bolts of the James Webb Space Telescope, the actual engineering of how this spacecraft will work. So what are we talking about anyway when we talk about the James Webb Telescope? Well, let's take a look at what it might look like. This is an artist's conception. And you can see that gold dish here, which is the actual mirror of the telescope. And below it is what we call the sun shield. And we'll get into that and why that's important in a moment. But as Irene said, it'll be the largest, most complex telescope ever launched into space. It will see further than the Hubble telescope ever did. Hopefully, it will show us the first stars and galaxies ever formed in the universe. Now, think about that. Before there were any stars, there was no light in the universe. It was total darkness. So the first stars turned on and there was light, and the rest is history. The telescope, the James Webb, will also show us the evolution of stars and galaxies as time goes on. And it also may be able to study the atmospheres of exoplanets, planets, possibly habitable planets orbiting other stars. So let's go on. What makes this telescope so special? Well, there are a couple of ways in which it is expected to outperform anything we've ever had in space before. So here is a comparison between the Hubble telescope primary mirror and the James Webb telescope primary mirror. You may notice that the Hubble mirror is a single block of glass. It's about 2.4 meters in diameter. The James Webb is composed of 18 segments that are put together as the telescope unfolds in space. The actual mirror blanks are made of a substance called beryllium, which is element that enables us to perform, to make very lightweight yet strong structures. This is a fraction of the weight of steel or glass, and yet gives us high performance. The telescope is also coated with a film of gold. And that's because gold is very good at reflecting infrared light. The amount of gold, though, I was really surprised how much gold is there when I found out. It's actually, if you took it all and wrapped it up, it would be the size of a marble. And it weighs about as much as a golf ball. So there's not a lot of gold there, but it's plenty enough to do the job. Now, let's look at the mirror itself and how it was constructed. So this is one of the mirror segments we're looking at. This is in a clean room. So all of the engineers here are wearing these, what we call bunny suits, to prevent any dirt or contamination or dust from falling on a telescope's array. And here it is fully extended. They're testing it for to make sure it extends properly. And in this view, it's compacted into the form it'll be launched in, so it can fit into a rocket. These gold panels have actual actuators that will enable each segment to be adjusted once the telescope is completed, and all of them will be able to be brought to a single focus. Another unique thing about this telescope is that it's going to observe in the infrared. Now here we're looking at the electromagnetic spectrum. Our eyes can only see the visible light, which ranges from violet to red, a very narrow slice of the electromagnetic spectrum. Shorter wavelengths, such as ultraviolet, X-rays, gamma rays, are not visible to our eyes. Neither is infrared, microwaves, or radio. We have instruments and equipment to detect all of these, but as far as our eyes go, we can only see visible light. Now, the James Webb telescope will function primarily in the infrared. So it'll be looking at the near infrared, near the visible spectrum, as well as the mid infrared. Now, it's important to remember that all objects in the universe that have a temperature above absolute zero emit heat. And heat is manifested in a form of infrared radiation. So everything with a temperature above absolute zero does radiate in the infrared portion of the spectrum. And that includes you and me, by the way. Another unique feature of this telescope is its location. It's going to be launched to a point called the Earth-Sun L2 point, which is actually, it stands for Lagrangian point. And as the Earth orbits around the sun, the L2 point, where the telescope will be, will also orbit around the sun, but it'll be about 1.5 million kilometers more distant than Earth's orbit. That's well beyond the orbit of the moon, but it is a stationary, stable, I should say, location where the telescope can gaze outward into space without the Earth, moon, or the sun interfering, because those are powerful heat sources and infrared sources. They would easily swamp the signal from the faint types of objects we are looking for with our telescope. This is basically just a schematic of the two sides of the telescope. So there's one side that will be perpetually exposed to the sun, and that's the hot side. On that side, we'll have solar panels, of course, that they need to be exposed to the sun. We'll have a communications antenna that looks back towards Earth. The computer and the steering reaction wheels, all of those are on this side, so any heat they emit will not affect the telescope. These regions are separated by what we call the sun shield. We'll get a better view of that in a moment. But that insulates the cold part of the telescope from the hot side. And in a cold side is where the science instruments and the actual mirrors of the telescope are. And here's a view illustrating a little bit better the sun shield. Up here is the mirror of the telescope with its 18 segments. This is called the secondary reflector, and the science instruments are actually behind here. The mirror captures light. The bigger the mirror, the more light it captures. So that's one of the reasons we need such a big mirror on this telescope. And then the light gets reflected onto the secondary mirror and back down in a column through this hole in the primary mirror back to the instruments that can analyze it. So all of this side is kept cold to minimize any source of infrared radiation from the sun, from the Earth, from the moon, even from the warm parts of the telescope itself. And of course, the warm parts are all down here on this side of the sun shield. The sun shield is really large. As I said, the mirror itself is 6.5 meters in diameter. The sun shield is much larger. It's about the size of a tennis court, about 22 meters in length on its longest dimension. And here you see a couple of engineers in a process of assembling this the sun shield, and this is the location where the telescope will be mounted through this hole, and the sun shield will be protecting all of that. These are actually very, very thin membranes, 5 membranes. We'll learn a little bit more about that in a moment. So after this summary, let's talk about what it takes to get a telescope like this operating. A project like this is beyond the ability of a single nation or space agency to create. So it's a collaborative international project with contributions from NASA, ESA, and the CSA. Now, in case you're wondering, ESA stands for the European Space Agency, and CSA stands for the Canadian Space Agency. And I assume you all know what NASA stands for. If you don't, just let us know in the Q&A, and we'll let you know. So this chart shows all of the different centers in the United States, in Canada, and in Europe that contributed to the development of this telescope. As I said earlier, it's a cooperative project with NASA, ESA, and the CSA. Now, what is ESA actually? A lot of people haven't even heard of it. So the European Space Agency is composed of a number of countries that have as a common goal the exploration of space, and they collectively undertake some pretty impressive projects. They're not exactly all members of the European Union. There's not necessarily overlap there. For instance, Great Britain is no longer a member of the EU, but it is and will continue to be a member of ESA, the European Space Agency. One of the contributions ESA is going to make is to provide a launch site. And the launch site is going to be in French Guiana, which is technically a French overseas territory. The launch site is going to be about here on a coast. And this is about 5 degrees north of the equator. Why is that important? Well, it really helps us because, as you can imagine, as the Earth spins on its axis, different parts of the world travel at different velocities. Somebody standing at the North Pole, even though they may be turning around, they're actually not making any distance. They're not, there's no lateral displacement there. On the equator, on the other hand, where the launch site is located in French Guiana, the Earth is already turning at 1,650 kilometers per hour. That's over 1,000 miles per hour. At the latitude of Cape Canaveral, where most of America's space launches come from, the rotation rate is lower. It's 1,550 kilometers per hour. The telescope we're launching essentially has to reach Earth escape velocity. It has to go well beyond the low Earth orbit or the orbit of the moon. So that's about 40,000 kilometers per hour. But because we have this free lunch of the Earth already rotating at 1,650 kilometers per hour, that already provides us with a small boost. So the actual launch velocity will only need to be 38,350 kilometers per hour. That doesn't sound like a significant difference, but it makes a huge difference in terms of the weight of the telescope that we can launch. This describes the journey of the Webb to its final location. Here is the Earth, the moon in its orbit around the Earth. So the launch occurs here. During the first month that the telescope is traversing from its launch site, I apologize, I'm getting well ahead of myself in my slides. So once the telescope is launched, it'll take the first month to reach its position at L2. During that first month, the telescope will unfold like an origami puzzle and assemble its sun shield, its optics, its solar panels, etc. By the time it reaches the L2 position, all of it should be deployed and configured. Now, it won't actually go to the L2 position itself, which is right here, because that's a little less stable than we would like gravitationally. So it will actually move in what is called a halo orbit around the L2 position. And once it reaches that position, after about a month after launch and enters into orbit, the instruments will begin to be turned on about 2 or 3 months after launch. About 4 or 5 months after launch, the instruments will be tested. And finally, 6 months after launch, we'll begin the routine science experiments. And as I believe Irene mentioned at the beginning, the official launch date for the telescope is October 31st, but I wouldn't be surprised if it got delayed into November sometime or even December. Now, the telescope has to fit into the rocket. The problem is the Ariane 5 and any other rocket available only has so much width it can carry in its payload fairing. So here you see the telescope folded up. You see 3 of the reflecting mirrors here. The rest of the mirrors are here on the side. The sun shield is folded up. The whole apparatus is folded up so it can fit into the launch fairing of the rocket. And just to give you a comparison of the scale of things, these blue silhouettes you see here are silhouettes representing humpback whales. That just gives you an idea of the size involved. Now, the Ariane 5, which has a width of 5.4 meters in its payload fairing, as well as the Atlas V, have the greatest payload fairing width. But you may remember the telescope mirror is 6.5 meters across. The sunshade is 21 meters across. So there's none of these will be capable of lofting the telescope in its final unstowed configuration. It will have to be compressed and put into this payload, so when it's launched, it can gently unfold like an origami puzzle. And let's take a look at how that deployment's going to work.
The Webb telescope separates from the launcher's second stage. The white ring close to the Earth represents the Hubble Space Telescope's orbit, and the larger orbit is the geosynchronous orbit where most telecommunications satellites are located.
I'm sorry, I should also point out, I meant to point out that in this video, on the bottom, you will see the progress of the telescope as it's launched from Earth, past the moon, and up here you will see the elapsed time of the mission. Sorry to start again.
The Webb telescope separates from the launcher's second stage. The white ring close to the Earth represents the Hubble Space Telescope's orbit, and the larger orbit is the geosynchronous orbit where most telecommunications satellites are located. The solar array is Webb's first deployment. When completed, all of Webb's electrical power needs are satisfied by the solar array for the remainder of the mission. The onboard control system continually monitors and updates the attitude to ensure power generation and thermal safety. To preserve the cleanliness of the mirrors, thrusters are located only on the sunlit side of the observatory. The trajectory is designed without employing a retrofire, which necessitates pointing the delicate telescope at the sun. If course corrections are needed, these velocity additions must be done early in the flight to most efficiently use the mission's limited precious fuel. After completing mid-course corrections, the Webb telescope passes the orbit of the Moon. Webb's initial transformation is the deployment of the sunshield pallets. The tower separating the telescope and instruments from the spacecraft and sunshield is next. Next, the aft flap deploys. This is key to managing momentum buildup and fuel consumption. This structure helps to balance the pressure from the sun's light on the Webb telescope around its center of mass. After the sunshield pallets reach their final positions, the membrane launch restraints are released. These have kept the sunshield membrane safely in place from final stowage at the Northrop Grumman facility in California through shipment and launch. The sunshield protective covers roll back, permitting membrane deployment. The covers over the core region release next. Then the mid-booms extend and the sunshield assumes its hexagonal tennis court-sized shape. It is now time to tension the sunshield membranes, each thinner than a human hair, pulling each of the uniquely sized and shaped layers to their optimal position. When deployed, the sunshield allows the telescope to cool to 385 degrees Fahrenheit below zero, cold enough to liquefy air, while the layer closest to the sun is almost 190 degrees Fahrenheit above zero, nearly the boiling point of water. It's of almost 600 degrees. Truly fire and ice. Once in the shadow of the deployed sunshield, the telescope and instruments continue cooling down to their final operational cryogenic temperatures. At the completion of membrane tensioning, the secondary mirror deploys into position and is latched rigidly in place. The aft deployable radiator releases and springs into position, allowing the instruments to radiate their waste heat directly into space and away from the telescope. Disposing of excess heat is crucial to the mission so that it does not overwhelm the faint infrared signals to be collected from the cosmos. The cord-fold wings deploy and latch in place, completing the major deployments of the largest telescope in space. As the Webb telescope continues out to its operational orbit around the Sun-Earth L2, the observatory continues to cool down to its final cryogenic temperature state. A trajectory correction applied 29 days after launch puts the Webb telescope into its halo orbit, a key part of the mission design. The Sun-Earth L2 point is where Webb's orbit around the Sun is synchronized with Earth's. At this point, 1 million miles from Earth, Webb is free from the thermal influences of the Earth and all eclipses. Additionally, the Sun, Earth, and Moon, the brightest objects in the sky, are hidden by the deployed sunshield, giving Webb a dark, cold, and stable environment to carry out its mission of discovery. Once the mirrors and detectors are sufficiently cold, the wavefront sensing and control operations can begin. This sophisticated multi-step operation's ultimate goal is to position each of the Webb telescope's movable mirrors into their correct final positions and orientations. Once the mirrors are aligned, the mission team will continue checking out the science instruments, preparing them for operations. Commissioning is completed about 160 days after launch, and the science mission is ready to begin. This brings to fruition the work of the thousands of members of the Webb team from the United States of America, Canada, and Europe. Astronomers from all over.
Okay, so that's a vision of the deployment. If all goes well, they had mentioned the instruments. Now, what instruments are actually on the telescope? Well, there's 4, and we can look at this diagram to see these clusters, each of which represents an instrument. So one of them is the near-infrared spectrograph, which will be able to evaluate the temperature, mass, and chemical composition of objects. That is a contribution of ESA. Then we have a mid-infrared instrument, which can observe very cold and distant objects. That is a collaboration between NASA and ESA. And we have a near-infrared camera, which can hopefully capture the light from the first stars and galaxies. That's a NASA instrument. And from the Canadian Space Agency, we get the near-infrared imager and slitless spectrograph, which potentially can find molecules in exoplanet atmospheres. And if we look a little more closely, these instruments operate in 2 temperature regimes. So again, visible light is over here from the violet to the red. These 3 instruments can see a little bit into the red, but mostly they operate in the near infrared. The MIRI instrument, which operates in the mid-infrared, actually needs to be much cooler. So that needs to be cooled down to 7 kelvins, minus 447 Fahrenheit. These instruments will operate at 30 kelvins at -4, which is minus 406 Fahrenheit. The sun shield is sufficient to cool these 3 instruments down, but the MIRI instrument at 7 kelvins will need to have a special active coolant loop of liquid helium in addition to the sunshade to keep it at the proper temperature. Now, there's more to a spacecraft than just the mirror and the sun shield and the instruments. There's a lot of subsystems that support the telescope's operation. Among them is the electrical power subsystem. We briefly mentioned the solar panels in one of the videos. So the telescope is powered by solar energy. The attitude control subsystem actually keeps the telescope in its proper orientation, primarily ensuring that the sun shield is blocking light from the sun, earth, and moon. The command and data handling subsystem, which is a fancy name for the onboard computer. The propulsion subsystem, which is a series of small rocket jets that will be able to make whatever small adjustments to the trajectory of the spacecraft over time will be able to perform. The thermal control subsystem, we already mentioned that with the sunshade and the differences in temperature. And finally, the communication system. The telescope is not going to do any good unless it's communicating with us. And just how does that work? So the communication depends on a NASA network called the Deep Space Network. And this is composed of a series of 3 very large dishes in Goldstone, California, Madrid, Spain, and Canberra, Australia. These are separated by about 120 degrees in latitude, in longitude, so that any spacecraft at a distance will have at least one of these antennas in view at all times. So how does the communication actually work? Well, let's say we start here at the Space Telescope Science Institute, which is the control facility at Johns Hopkins University in Baltimore. If they want to send a command to the telescope, it would travel from there to, in this case, Goldstone. This is just an example. It could just as easily travel to one of the other 2 telescopes in the Deep Space Network. The radio telescope will then send a message 1 million miles away to the James Webb. The Webb will do what it's told, make whatever observations necessary, and send the data back down to one of the antennas at the Deep Space Network. And that information will again be transferred to the Space Telescope Science Institute Control Center. Here's a view of the Space Telescope Science Institute, the Science Operations Center. You see several women here at their screens, I assume doing some sort of simulated practice run for use once the spacecraft is launched. And the observations obviously with a telescope this powerful and this capable, there's going to be a lot of demand from the astronomical community for observation time. And however, the time is limited and has to be prioritized. The telescope can only do so many things at once. And the mechanism for that primarily is going to be the General Observers Program, where astronomers from around the world will be able to submit proposals that will then be peer reviewed and decided upon by a time allocation committee. In cycle 1, which is the first year of operation, 266 proposals have been approved for that time period. And I believe they're now evaluating proposals for cycle 2 and 3. There's another method of getting observations from the telescope called the Director's Discretionary Science Time. This is primarily for unanticipated observations. So for example, if there's a supernova explosion or a black hole merger, that's the kind of thing we want to prioritize right away because it's a time-sensitive observation. We have to do it then and there, so that will be a priority. There's also a third category for the first 5 months only. There's a guaranteed time observation. This is only for scientists that have already actually worked on the telescope. And it's primarily intended to demonstrate the capabilities of the types of observations the telescope can make. 13 programs have been approved, including observations of objects in the solar system, exoplanets, galaxies, quasars, and so forth. So that will be some of the first science we wind up seeing from the telescope. So let's get ready for this telescope to be launched. And I'm very excited about this. So let's watch the telescope as it's on its way. Here's the launch on the Ariane 5 from French Guiana. There it goes. and is ascending through the atmosphere on its liquid core engines and its two solid rocket boosters on the side, clearing the cloud layers. The side boosters are going to burn out, separate from the main booster. And the telescope, it's on its way to wonderful discoveries about the universe. And so with that, I'm going to end the presentation, but I do want to bring up this slide. Renee talked about this earlier. So these are upcoming events. On September 15th, we're going to have the last of these three talks specifically about the James Webb Telescope. We're going to be discussing some of the things that we hope the telescope will show us, and maybe some of the things we may not expect the telescope to show us. On October 15th, we're going to have an in-person event at the Krista McAuliffe Center, and we are going to have a guest speaker, Dr. Catherine Flanagan, astronomer emerita at the Space Telescope Science Institute. She will be working directly with the telescope before, during, and after launch. So she will be a resident expert that we really want to tap into. And by the way, this is an official NASA-sponsored Webb Space Telescope community event. And last but not least, at a date to be announced, we are going to have a launch party. We don't know exactly when that is, but we will be gathering together to actually watch the launch on a day of the mission launch. So with that, I am going to turn it over to Irene and a Q&A period. So if you have any questions, please type them into the Q&A, and I will be glad to try to answer your questions as best I can.
Wonderful. Thank you so much, John. This was so informative and so exciting. Again, for all those who have questions, please feel free to post them in the Q&A in the box in the lower right on your screen, on your Zoom screen. I wanted to say, John, seeing that, of course, simulated launch at the end, right? It made me really think of this. It's time. We want to see the real one, hopefully soon. But, you know, again, it's great to really get the charge just by watching the video and waiting to see what will happen. Also, you made me reflect on the first observation that will be made. These are going to be really requested by the scientists that have been working on this project now. For some of them, it's really for about 20 years. So it's going to be really exciting for them to see their science to be finally being done, right? Not just as a theory, but data being collected and see what they have to reveal to us. But again, as we are waiting, I actually have a question for you, John. I mean, I know we've been talking this past couple of months a lot about James Webb. What is one thing that is really surprising to you or exciting for you about the mission?
Oh, that's a great question. There's so many things that are exciting about the mission to me, but I think the most exciting thing is the potential to actually see the first stars and the first galaxies that ever formed in the universe. That's beyond the reach of present telescopes like Hubble, but we think that with the James Webb, we'll be able to see that far back in time that we can actually see the first formation of stars.
Wow, yeah, that is something really exciting. You know, I read some articles where we're really describing we were going to see our beginnings, meaning it's not just of us here on Earth, where really we are going to peer into the beginning of the universe itself. All right. Here is a question. Oh, great question. It says from Pat. Hello, Pat. How long, for how many years, is the Webb telescope expected to last and send back information to us?
Oh, that's an excellent question. So the main limiting factor on a telescope is actually the amount of attitude control fuel it has to keep itself properly oriented and aligned. And the expected lifetime of the telescope, the minimum lifetime is 5 years. But there is actually enough fuel in the attitude control system to keep it operating at least 10 years. So I am confident that we will get at least 10 years of operation out of this telescope.
Wow.
Thank you for that question.
Yeah. And you know, I mean, we can see how long that Hubble Space Telescope, after being repaired and being serviced a few times, of course, that's a big difference, right? But it's been going strong for so many, 25 years, more actually, 30 years almost.
Like 31
So,
years, yeah.
31, yeah. I remember, actually 25 years was when I first joined the McCullough Center. A year later, we actually celebrated the 25th anniversary for Hubble. So, okay, that's been quite exciting. Again, if, you know, we are, I know there was a lot of information was shared with you, but I think John really did a good job in linking everything together. So simple questions are welcome. Questions about other aspects of either of the mission, the science, they are all welcome. Well, I'm sure John will do his best to address them. But otherwise, John, I have another question. I know we talked a lot about the mirrors. It was, I mean, the main mirror, the primary mirror. Can you tell us a little bit more? I mean, it's kind of a complicated system. It's going to unfold and then position. What's going to happen there? What is really going to happen with the mirror? And how critical it is that all these segments are well aligned?
That's an excellent question, Irene. And it is very critical. So as you have seen, we have 18 individual hexagonal segments to comprise the main mirror. Now, when they launch, they may and unfold, it may be difficult for those to remain properly aligned. So there are actually actuators, tiny motors on the side of each of the hexagonal segments that will fine-tune the adjustment to bring the focus to the same place from each of the mirrors, and that'll be part of the deployment stage prior to the first observations.
Right, because even the smallest misalignment in the position of those mirrors could ruin actually the all capability, like for example, could ruin the imaging quality, the quality of the images that the telescope will take. So that it's really critical. We are talking about aligning these mirrors at the fraction of the micron, you know, it's smaller than the cross section of our hair, at 1 million miles away from here. So it's quite incredible. Oh, we have a very interesting question from Stephanie. Who was James Webb and why does the telescope have this name? Always an interesting question.
It is an interesting question. James Webb was actually not a scientist, not an astronomer. He was the administrator of NASA during the time when the Apollo program was getting ready to launch humans to the moon. So this was in the 1960s. when President Kennedy made the directive to land men on the moon and return them to Earth safely by the end of the decade, James Webb was the individual, the administrator who organized the far-flung centers of NASA, all the companies and industries involved, all the people involved, organized it all in order to enable the first six landings on the moon that happened. I believe he actually resigned just prior to the first landing on the moon, but without his help, it probably would not have happened.
All right. So, okay. So I think this question will keep coming because it's really not a well-known character in the history of this space exploration to the general public. Of course, within the field, people know who it is. Okay, this is a great question. It's actually a two-part question. So the first part is that I will read both though, John, so you can figure out what to answer. But the first is, how are we going to see our past with this telescope? And the second part is, how are we going to see the first galaxies?
Good question. And they are both related questions. When we look out into space, we're also looking back in time. And that's because light from any objects we see takes time to reach us. So if you think about the sun, the light from the sun actually takes 8 minutes to reach us. So we're looking back to see the sun really as it was 8 minutes ago, not as it is right at this instant. And the further back you look, the further back in time you're seeing these objects. So when we're looking at these very faint galaxies that are, I guess, about 13 billion light years away, we're actually seeing 13 billion years into the past. And that's about when our universe began. The Big Bang is estimated to have happened about 13.65 billion years ago. And we are getting close with this telescope to the formation of the earliest stars right after the Big Bang. So we're looking at a great distance, and because of that, we're looking far back in time towards our very beginning.
So Caroline, that was a great question. And I see that you are a high school student at Brockton High School. So really, thank you for asking that great question. Just as a corollary, John, and this is why Webb is special, is because in order to be able to look at very faint objects, really need very, very big mirrors. And this is the largest mirror that we ever launched into space. So because it's such a large mirror, we'll be able to see these very faint objects. They are very far away. And with that, the way we see them is how they were really at the beginning of the evolution of the galaxies and almost at the beginning of the universe, almost. But thank you, that was a fantastic question. Oh, and then we have another, I'm not saying tricky, but interesting question here. When Webb gets to the end of its mission, so what's going to happen to the telescope? I honestly don't know, but I wonder, John might actually really know because he knows all these cool things. Do you know if the gravitational pull of the Earth or of another body will pull it, for example, in this case, will be pulled towards Earth and will burn into the atmosphere, or what?
Well, as I mentioned, the orbit around L2, that halo orbit, is what we call metastable. So it you can stay there for a long time without applying any corrections to the orbit. But eventually, once the fuel is used up, as we mentioned, is going to happen at some point, the telescope will no longer be able to remain at that L2 position. So your question is what's going to happen after that? And I don't know the answer. I haven't read about the answer, but I suspect that because it's so far away from Earth to begin with, it won't re-enter Earth's atmosphere. It's not an orbit around the Earth, it's an orbit around the sun. So I suspect it'll drift off into its own independent orbit around the sun. And we will undoubtedly lose track of it at some point or another.
I'm taking note, though, for when Kathy Flanagan joins us on October 15th, we had to make sure to ask her this question, assuming that we don't find the answer before then, but it would be cool to ask her about that. And I just see that there was actually a question in the chat that I apologize, I didn't see it because I was only looking at the Q&A. This is another interesting question, probably is going to be the last one for the evening, but the question is this: will there be a latency in transmission of signals from Earth stations to the telescope? A delay between during the transmission of signals?
Yes, there will. I'm not sure exactly what it is. I know to communicate, to send a signal to the moon takes about 1.5 seconds. And this telescope is about, well, let's see, about 4 times further than that. So probably in the neighborhood of 5 to 6 to 7 seconds one way will be the latency time. I'm just guesstimating. I don't have a solid answer to that, but it's about that order of magnitude. And of course, the signal will take just as long to return to Earth.
In general, though, this kind of delay is not a big issue with this kind of missions. Obviously, I mean, if something is going wrong and you want to act quickly, any second counts. But in general, because we are sending commands, knowing where the telescope is and saying how to change, some of its tiny changes to the trajectory, or just to receive the data back, like the images and the spectra of the telescope receive. Usually that is not a big issue. But yeah, definitely needs to be taken into account, right? Okay. I guess this is going to be the last question of the evening because it is funny, though. Not funny, but it's interesting. What is and where is the observatory behind your head, John? the picture in the background.
It is just a Zoom background. Let me say that. I'm not really here. It's a picture of Mauna Kea in Hawaii, which is one of the sites where some of the biggest telescopes in the world are located. And I personally, my thing is I love sunsets. And so I wanted to use this picture with a sunset over the observatory on Mauna Kea in Hawaii. But actually I'm sitting in my bedroom in Cambridge, Massachusetts.
Oh, well, we can always dream, right? All right. I see actually we passed our 8:30 mark, so I think it's time to wrap up. But I really want to thank John again for a very interesting presentation. I want to thank you all for joining us tonight. Just a quick reminder to everyone that our next presentation with John about the science of James Webb will be on September 15th. And then, I really want you all to remember, talk to your friends, to anyone you know, and mention to them that, of course, on October 15th, we are doing this major event, special event, really, in person at the Framingham State Planetarium. The event will also be live streamed. So we really hope to have a full house. We will all be masked. So we will all, of course, follow all the safety measures that we need to. But we really hope to have a full house in person and to have many, many other people join us via live stream. So check our website. And I see, thank you, Suzanne, for posting the website again. It's going to be an historical moment. The launch of this telescope is going to be an historical moment. So I hope that it will help all of us think about something a little bit more like hopeful, but unfortunately, some of the news that we hear on TV often these days, right? So I really hope that the launch of this mission is helping us look forward with, again, hope and vision and aspiration. So we will do our best to share the word, the information about these new events with everyone. And we would love for you guys to help us share the information. But with that, I want again to thank all of you and wish all you good night.
Thank you, everybody, for joining us. It was a pleasure.